In this video, I'm going to talk a bit about the Larmor precession of a spin half particle. And so precession just means that when our particle is in a magnetic field, so a uniform magnetic field, which is represented by this B sub naught here, then it's not actually going to point directly along the path of B sub naught. And so this is going to happen because the particle having a spin is actually giving it a magnetic moment. So a magnetic dipole moment, which is actually this right here. And so that's represented by this I right here. And so we see that's some angle away from our actual magnetic field lines. And so then this omega here is telling us that it is actually rotating around. And so omega is actually the frequency that it rotates around. And so I'll talk about that a little bit at the end of this video. So just to get a little bit more intuition of what a precession is. So we can look at sort of a globe of the world here. And so we see that the North Pole is pointing the at the North Star up here. But this does precess, and so you see that this can go over here so that it's actually pointing at 23.5 degrees from sort of straight up and down with respect to our solar system that way. And so the sort of North Pole can actually precess around. And so you'll also see that with a top over here, where if you've ever spun a top, you sometimes see that, especially when it starts slowing down, it starts sort of wobbling, and so that is the precession of the top. And so that is sort of what we're talking about here, but we're talking about it with respect to the magnetic dipole moment of a spin half particle, so something like an electron, but also the nucleus actually acts as a spin half particle. Well, a proton does because it has it has three quarks, and two of them the spin will cancel out, and then the last one its spin will not be canceled out, and so quarks have a half spin, and so a proton will actually have a spin associated with it, which becomes important, for things like nuclear magnetic resonance imaging, which, you know, I'm a chemist. That's my background, so that's sort of, where I've kind of run into this stuff here is when it comes to NMR or nuclear magnetic resonance. But anyway, let's get into this. So the magnetic dipole of a spinning charge is this. So it's this gamma times I. So I is the spin angular momentum. So Griffiths actually uses an S for this, but since the image that I got was using an I just used I instead. And then so gamma is the gyromagnetic ratio. And so I explain that a little bit here. So for a spin half electron, the gamma is equal to minus E, where this E is the charge, for an electron would be negative. The M is the mass. This G is actually the G factor, which I'll talk about here in a second. So it is a unitless proportionality factor. So in classical physics, gamma is equal to Eg over 2m because G is just equal to 1. And so it's usually written like this. But in quantum mechanics, relativistic effects actually make gamma around twice as strong, and so that's why it's missing that 2 in the denominator here. And this is because for a spin half electron, G is equal to about 2, and so the 2's here kind of cancel each other out, and we just end up with this minus E over M. And so the G factor is actually that thing that's like, extremely highly sort of accurately measured, and it's just a little bit above 2. It's like, I think it's like 2.00 something something. I think numbers start there, and it's measured to within like a 10 to the minus 13 accuracy. And so yeah, that's what that number is, and this is sort of where it gets used. And so it's one of those things that scientists like to talk about because it's measured so accurately. And I think recently they've found a deviation in it with the muon, which is sort of an exotic type of electron, but that's getting outside of what we're talking about here. All right, so this spinning is, causing a torque because torque is sort of the force of a spin. And so the energy associated with the torque is this H, which is minus mu dot B, where this mu is like I said, the magnetic dipole up here, and B is the magnetic field that our particle is in. So yeah, B equals our magnetic field. And so we can make a Hamiltonian operator that is our minus gamma B dot product with our sigma, where sigma is the spin matrix, and it's bold, so it's actually what's called a vector operator, where we can actually put matrices into a vector like this. And in the previous video, I mentioned another video from another YouTuber where he derives the Pauli spin matrices in a different way, and he actually looks at it more using this sort of formalism instead. And so that's kind of where that comes from. And so more explicitly, if we want to sort of show actually the components of this magnetic field and the components of our vector operator. So we have our minus gamma, and then we have the three components of our magnetic field, and then our three Pauli spin matrices. So even more explicitly, so we see that we have the Pauli spin matrices in here. And so we're going to look at this in a uniform magnetic field. So this little figure here is supposed to show kind of what that is, where the magnetic field lines are sort of perfectly straight here. And so you can see that in here they have the little alpha. They are using S for the angular momentum there, and then they have B here for their magnetic field. And so we will use a magnetic field pointing in the Z direction, so our B is just the Z direction, so we actually put zeros in for the X direction in the Y direction, and so it will actually cancel out with this one because it will multiply by that zero, and cancel out this one because it multiplies by that zero. So we have our minus gamma, our BZ, multiplied by this, and so that ends up giving us that right there. And so this is our Hamiltonian operator when we are in a uniform magnetic field pointing in the Z direction. So we have our eigenstates, which once again are the chi plus and the chi minus, which is just the basis vectors here, or the basis spinners rather. They have an energy of E plus, so that's associated with our chi plus there. And so that's just the negative of this right here. And so then the E minus is just the positive version of that. And so we act our operator on the spin up here, and it gives us this eigenvalue here. And so we show the Hamiltonian operator more explicitly right here, and then make our spinners explicit right here. And so we see that we have this will sort of distribute into here. That will multiply by this one. This negative one will just get multiplied by that zero. And so we just end up with this times a 1 here, and so that is how we end up getting that. And so then if we do it for our chi minus here, which is our spin down, then we have this right here, which is negative kind of getting distributed into here. This 1 will just get multiplied by that 0. This will get multiplied by that 1, and so we have a negative times a negative here, so that makes it positive, and so then we have this. And so we see that this shows that the energy is lowest when the dipole moment is parallel to the magnetic field, which is this right here. And the energy is highest when it is anti-parallel to the magnetic field, which was this right here, because it's positive energy. All right, so the time-dependent Schrodinger equation. So we want to think about this precession, which is going to happen in time. So we have to use a time-dependent Schrodinger equation, and we can use a general solution for this. And I've talked about solutions to the Schrodinger equation in previous videos, but we have this general solution. So A and B here are some sort of constant. And then we have our e to the I times e plus t over h bar, and then our e to the minus. So this should actually be plus here. That should not be negative right there. And so then we can just put it into this spinner form right there. And so when our t is equal to 0, so the t's will be equal to 0 in here, it turns those e to the power of 0 into 1. So we just end up with this. And we can use a equals cosine alpha, where alpha is that angle here away from the magnetic field line. So it's the angle of our vector for the angular momentum, the angle that is away from the magnetic field line. And so we'll use this this a equals cosine of alpha over 2 and b equals sine of alpha over 2, and so we can then substitute those in for the a and b there, and we end up with this. And so we want to calculate the expectation values for the spin angular momentum I as a function of time using our operator here. So this is our X spin operator. And so I actually went through and did a lot of the math here. So in Griffiths, it just kind of goes right from here down to here, skipping all the math here. And so I've just, I've made this substitution into here. And so then I've made it explicit. So putting these in. So we see that this one ends up getting turned into a negative because we're doing a row vector, which makes these into the complex conjugate. And so this one becomes a plus. This stays positive here and negative here. So we, I factored that out, and then I just acted this this matrix here onto this, and so that just flips these two things around because we have these two off diagonals here, and so we end up with this. Then I multiply this left by the top and this right by the bottom, so we end up with this next step here, which looks like a kind of a mess, but we can factor out these cosine alpha over 2, sine alpha over 2, since those are common to both of them. So we factor those out. And so then these combine together. So because we have a minus here and a minus here, so we just add those two together, which gets rid of the factor of 1/2, because 1/2 minus 1/2 is minus 1, which gives us this right here, and then plus 1/2, or plus 1/2 gives us this right here. Then we use this trig identity, so 2 times cosine of whatever is in our argument is equal to these right here. So this is just a trig identity I looked up on Wikipedia, so that's just a trig identity. And so we just substitute our 2 cosine in for this, and since that 2 here will cancel out with that 2, we just end up with this right here. So then this cosine alpha over 2 sine alpha over 2, I just used more trig identities that I found on Wikipedia, and that's what's in this box right here. So then I just multiply those two things together. We get this. So then I just FOIL these two things. The cosine alpha minus cosine alpha cancel out. So we end up with this, which another trig identity, 1 minus cosine squared is just sine squared. Then we just take the square root of that and we end up with this. And so then we sort of substitute that back in for these things. And so we end up with what Griffiths just kind of jumped right to. And so here I've kind of gone through the whole math. And I'm going to leave a link to my show notes in the description down below. So if you want to sort of study this in a little bit more depth on your own, then you can go ahead and do that. And if we did the same thing for our y and our z component, so remember up here we're just looking for the x component, and so this right here in this pink was just the x component, and these are the y and z components. And so the thing to notice is that our x component and our y component both have this cosine and sine with a t in it. So those are actually a function of time, where our z one does not have any function of time. It's just this, which is a constant, and so it remains at a constant angle alpha with respect to the BZ component of the uniform magnetic field. And so what that is telling us is that we have this wobble where this angle from the B here stays, that stays constant, but it's sort of changing, in the X and Y directions, over time. So it keeps changing over time. And so it moves in the XY plane as a function of time. And it will spin at a frequency known as the Larmor frequency, which is this. So that is that omega, which this shows right here. And so the L here is just telling us that it's going in a left-hand direction. So we have this, and it makes sense that we'd have this, that the frequency at which it would rotate is based on the strength of our magnetic field. So it's based on, how strong the magnetic field pointing up is, and on the strength of our dipole here. And so those two things together will determine the Larmor frequency. And so that is everything on the Larmor frequency. Once again, just the take-home message after all the math is just that the angular momentum, which is pointing along the direction of our dipole moment. So we see that this here, that we aren't having any change in direction. So the dipole moment is pointing in the same direction as our angular momentum. And so that is some angle alpha away from the actual magnetic field lines. And so in the next video, I'm actually going to talk about the Stern-Gerlach or Gerlach. I've only ever seen that written experiment, and so that is using a sort of non-uniform or inhomogeneous magnetic field, which then we don't just have this torque here. We don't just have the torque on our dipole. We actually have a force on it, and that's actually what causes sort of the splitting. When we pass it through our magnet here, it causes a split based on whether it's in spin up or spin down. And so I'll talk about that. I mean, I've talked about it in previous videos quite a bit, but I'm going to talk about it, I guess, from kind of a different angle, sort of the angle found in Griffith's quantum mechanics textbook. Anyway, I hope you found this video helpful, and I will see you in the next one.